So let's get started with our next set of talks. So I'm Dr. Jess McIver. I'm a new professor in the Department of Physics and Astronomy at the University of British Columbia. And first up, we have Alessandra Corsi. Dr. Corsi is an associate professor in the Department of Physics and Astronomy at Texas Tech University. She studies multi-messenger time-domain astronomy and gravitational wave physics. And she's going to be telling us about stellar compact object mergers and short gamma ray bursts. Dr. Corsi, please go ahead.
Okay, thanks for the kind introduction and everyone for having me here today. I'm going to be giving some highlights about stellar mass compact object mergers and short gamma ray bursts. I will be mostly focusing on this topic in the context of multi-messenger astrophysics that can be done with gravitational waves. And I should say right away that in such a short talk, it is almost impossible to really acknowledge and give credit to the many scientists who have been working on this topic. So please keep that in mind as I go through my slides. So first of all, there would be no multi-messenger astronomy done with gravitational waves without the LIGO and Virgo detectors. Here I'm showing the general network of ground-based gravitational wave detectors. Now, the kilometer scale ones are the two LIGOs and Virgo, but CAGRA has recently joined, and these three separate collaborations are really starting to work together. And I'll talk a little bit more about the future and LIGO India later on. We cannot talk about multi-messenger astrophysics done with gravitational waves, of course, without mentioning the star event GW170817, which of course many of you are familiar with. On the left side plot, you can see the gravitational wave time frequency track that was left in the detectors by these in-spiraling neutron stars up until they merge at time 0. And about 1.7 seconds after the event, a flash of gamma rays or a gamma ray burst was observed. Here the Fermi light curve is shown, but it was observed also by the integral satellite. So this was the very first detection of in spiral from a binary system of neutron stars associated with a gamma ray burst. So it confirmed the origin of what we call short GRBs, but it gave much more information than just that. A key element in this discovery was the localization. So in the middle plot, you see the error uncertainties in the localizations coming from gravitational waves and Fermi combined. Ultimately, the event was localized to an area of the sky of about 28 square degrees in dark green. And although this might seem huge, in reality, it was relatively small thanks to the fact that the Virgo European gravitational wave detector was taking data. And so about 11 hours after that merger, the SWAP team identified a dot of light in a host galaxy located about 40 megaparsec away. And this optical detection, in reality, an infrared optical UV detection, revealed something really fantastic, which is what we call a kilonova transient, or a quasi-thermal transient, which evolved from blue to red wavelengths over the timescale of a few days to 10 days, and demonstrated basically the origin of gold and platinum or heavy elements in the universe in association with binary neutron star merges. This was not the end of the story. A GRB was detected, and so the hunt was on for an afterglow. The hunt in reality started both at radios and X-rays pretty soon after the event, but it required some patience. So on the right-hand side, you see the Hubble Space Telescope image of the host galaxy, and then superimposed on that in blue is the Chandra image of the field, and that dot there is the X-ray counterpart to GW170817. So this was an X-ray discovery that came about 10 days after the merger. And then with the Jansky VLA, After waiting patiently for about 2 weeks, also we unveiled a new dot of radio light, and the brighter dot that you see in the images is the nucleus of the host galaxy. So even though this radio to X-ray afterglow was unveiled, it looked very different from normal cosmological gamma ray burst afterglows. You can see the light curves in the lower panels. The key point is that the light curve was observed to rise and then peak at a time scale of order 100 days after the event. So this was very different from the normal parallel decay of short GRBs afterglows, and showed us that this wasn't just the first direct detection of gravitational waves, the first identification in conjunction with electromagnetic radiation, but also the very first off-axis GRB jet, which is something that astronomers had been searching for more than 20 years. And the hunt in radio and X-ray wavelengths is still going on for potential delayed counterparts in those wavelengths from the same ejecta that generated the kilonova. Other highlights that are important to give are certainly in the radio, and I'm going to be focusing on that later on also, is the fact that VLBI gave extremely important evidence for the fact that radio emission was coming from a component different from that ejecta that created the heavy elements in the kilonova. So as you see in the cartoon, there was a jet emitted close to the speed of light, but the big deal about it was that we were observing this jet off axis. So about a 5-degree jet observed at about 20 degrees angle. And this created a shift in the centroid of the radio emission in the sky, as shown on the left panel, which was measured by VLBI. And so that was the key direct evidence of the existence of such jet. Now the constraints that are coming from the observing angle, in particular with VLBI observations, are going to have and are expected to have, with more detections, impact on cosmology. On the right-hand side plot, you see that there's a degeneracy between the measured distance and the observing angle with gravitational wave observations alone, which are the yellow contours. When you combine that with electromagnetic information, both in terms of light curve and VLBI imaging, you reduce that uncertainty to the blue contour. And so what this means is, in the future, with more detections such as GW170817, one could eventually solve the tension in the Hubble constant measurement between current Planck CMB and Cepheid supernova constraints. So we certainly want more events like GW170817, and so we can take a quick look of what are the results so far from Advanced LIGO and Virgo, which just finished their so-called third observing run. It was in reality suspended a month earlier than expected because of COVID. But there are two highlights that are worth giving of two events that have been confirmed so far: GW1908-0425 on the left and GW1908-14 on the right. The highlight about the first event is that if you compare the total mass of the system, this binary neutron star system, with what we know about binary neutron stars in the galaxy, which is the gray shaded area, it clearly showed that it is a heavier system regardless of what assumptions one makes on the spins, which are the orange and the blue curve. And then the other highlight from GW1908-14 is that this is merger between a black hole, so an object of a little more than 20 solar masses, with a second object, which we don't quite know whether it is a neutron star or a black hole. It is certainly an object in the mass gap around 2.6 solar masses. And so these two events are, what has been published so far. Of course, not everything is out there and published yet, so there's more results that we expect. But the fact that we know so far is that among these two events, at least, there was not another GW170817. So no credible AM counterpart has been found for those two events. So we certainly want more, as I said, of GW170817. And so looking into the future, what is in front of us is very bright. So the LIGO detectors will reach their nominal sensitivity, or are expected to reach their nominal sensitivity during their 4th observing run. And then they will transition to the so-called LIGO A+ configuration, which will bring the projected horizon distances for binary neutron star mergers even further, about a factor of 5 in terms of improvement in compact binary mergers detection rates. And then LIGO India is also foreseen to be brought online on those timescales. And so here we're talking about the second half of the next decade. Even further along the line, the 3rd generation gravitational wave detectors, such as the Einstein telescope or cosmic explorers, are concepts which are aiming at bringing down the sensitivity of gravitational wave detectors by a factor of 10, as you can see in the middle plot. So overall, what this means is if we focus on LIGO A+, as you can see on the right-hand side schematic view, we're gonna be able to detect neutron star binaries up to distances of order 500 megaparsecs, redshift about 0.1. And so it is important that the progress in gravitational, in gravitational wave detectors is also accompanied by progress in electromagnetic facilities. And so here I'm highlighting in particular the role of the next generation very large array. You can see on the left-hand side plot the improvement compared, for example, to VLA and ALMA in terms of angular resolution. And then it's going to be basically 10 times the sensitivity of the VLA. And so as proxy of that, the right-hand side plot shows a comparison in terms of effective collecting area. And is this necessary? Absolutely. It is fundamental that facilities such as the NGVLA come online. And this is shown in this slide here. So on the left-hand side plot is the GW170817 associated kilonova in the near infrared, the black line, and then projections for a variety of models is in the shaded areas. Different colors are for different redshifts for what these type of signals would look like when when we bring them farther. And so this already highlights that we're going to need extremely large telescopes in order to be able to follow the kilonova part. But even more for the radio emission, if you consider a GW170817 like transient, and you shift it at a distance of 500 megaparsecs, which was the reach that I showed you about LIGO A+, you can clearly see that we're going to need the sensitivity of the NGVLA, so 10 times better than the VLA is going to be crucial for further discoveries. And I want to end here. Thanks for your attention. We look forward to populating more this diagram of masses in the stellar graveyard and hopefully having more GW170817 events. Thank you.
Thanks very much for a great summary, Alessandra. So we have quite a few good questions in the Q&A here. I'm going to read you one. So in the case of GRB 170817A, we know that it originated from a binary neutron star merger. Is it possible to probe other possible progenitor channels of short GRBs, i.e. neutron star black hole mergers, based on their prompt emission or afterglow or other host properties?
Yes, so this is an excellent question. Indeed, systems such as neutron star black holes are the ones that remains the most elusive so far, at least in terms of potential joint gravitational wave and electromagnetic radiation. There are several different signatures that one would expect in a system like that that people are studying. Those go from, in principle, trying to study the physics that is encoded in the delay, for example, between the gravitational wave radiation and the gamma ray flash, but also from the afterglow. The properties of the kilonova are going to depend on the dynamics. And so there are signatures that a neutron star black hole would leave differently in that part of the emission from a binary neutron star merger. Obviously, all this is subject to uncertainties in the equation of state. And then later on, how much fast ejecta from the kilonova, and so how much late time radio flare will also depend on that dynamic. So yes, the answer is there's several different ways in which one can have a signature of a different dynamics in the merger in the electromagnetic radiation. And so far, we're looking forward to an actual observation of that.
Thank you again, Alessandra.